more probability. So last time we saw this nice thing called the multiplication rule. And if you happen to have independent events, nothing could be finer. The formula for the rule, if you will, looks something like this. The probability of A happening and then B happening, although I suppose they could happen at the same time, like if you roll two dice, they could happen at the same time. But anyway, I always think in terms of A and then B. Let's fix that. Is you take the probability that it, heads on the first flip or whatever, times the probability of, like, heads on the second flip or whatever. So you just multiply the two probabilities together. That's cool. Now, there's a big assumption that goes with this formula. It says if A and B are independent events, or you could say independent outcomes. Same thing, right? A and B have to be independent. The result of one has nothing to do with whether the first happened. They don't influence each other. One coin does not influence the other, kind of like that. But I do want to make that point. Let's just make that point. I'll say, P.S. in a statistics class especially, actually in lots of classes, but when using formulas, in this class in particular, because we have a lot of formulas. So when using formulas, check the conditions for them to apply. Conditions where they apply. Don't use the formula if it doesn't, how do you spell apply? Here we go. Don't use the formula if you don't have the right conditions. That's the idea. So it's not going to be so important today maybe, but it will be important as we move forward. So just be aware of, there's conditions on this formula technically. A and B should be independent events. Okay. So here's just an example, and this was, this is stuff we were doing last time again, so it should be a nice review. But it says it's a 4 in 5 chance, which is another way of saying it's a probability of 4/5. It's a probability of 4/5. Might as well move that front and center here. That at Christmas there's going to be snow on the ground. So find the probability that this actually happens every year for the next 15 years. So what you're saying is it's going to happen 15 years in a row, or that's what you're hoping for anyway, 15 years in a row. What's the probability that'll happen? Well, if it's a 4 in 5 chance every year, and we presume every year is going to be independent of every other year, whether we had snow last year isn't going to affect whether we have snow this year. So really we have to do this times itself 15 times in a row. 15 times, holy cow. Or, as a shortcut, instead of having to do that, let's see, how do you delete? Oh, awesome. We can say, well, if I'm multiplying 15 times in a row, that's the same as putting an exponent on it. So if you do that out on your calculator, I invite you to try it. Make sure you get this result. 0.035184 would be the decimal approximately. And if you move your decimal over 2 places, you'll get just about, 3.52% if I round it a little bit more. Something like a 3.52% that it could happen 15 years in a row, which to me doesn't sound like a really bad chance. It's not a good chance, but it's not like saying, oh, it's like a 1 in a million. No, it's actually a 3.5% chance. That doesn't sound so bad to me. So while I'm on this problem, how would you type this in your calculator? I find that a lot of people, they love their calculators, but that doesn't mean that they don't make mistakes with them. You have to be aware of how your calculator works, and your calculator uses this thing called order of operations, and if you're not hip on the order of operations that your calculator is following, you can end up with messed up results. So on my calculator, how did I enter this? I went like this. 4 divided by 5, right? That's what this is, 4 divided by 5. And then, before I raised it to the 15th power, I hit the equals button to get a result. And of course my calculator said 4/5, or it could say 0.8. Then I used my exponent key, 15, and I hit the equals again. Okay, and that's how I got this answer. Now, you could also, if you like the parenthesis buttons, you could do parenthesis 4 divide by 5, close parenthesis, and then raise to the 15 power and hit equals. So if your calculator has parentheses on it and you like parentheses, you could do that. Notice something though. 1, 2, 3, 4, 5, 6, 7, 8, 9 keystrokes. 1, 2, 3, 4, 5, 6, 7, 8 keystrokes. See? The old ways are better. So this is 8 versus 9 keystrokes, which might not sound all that amazing, but 8 versus 9 keystrokes. Sometimes doing things the old ways are better. You had to do it like this in the old days because for a while they didn't even have parentheses on the calculators. Anyway, why is this important that I hit this equals here? It's important because if I didn't, then it would have raised the 5 to the 15 power. I don't want just the 5 to the 15 power. I want the 4 divided by 5 to be a result, and that result raised to the 15 power. So the parentheses is one way of saying, hey, first get this result. The other way of saying first get this result is to simply hit the equals button. Okay. So anyway, just to keep that kind of stuff in mind. Got to be careful with these calculators these days. Oh, goodness. Okay, anyway, that's old. Let's get to the new. Dependent. We're going to use multiplication rule again today. I do like the multiplication rule. But we're going to start playing with what's called dependent events. One of the outcome of like one event, actually the chance does have a bearing on what happened already in the world. So for example, Biff randomly draws 2 cards, and here's the key phrase, without replacement. What does that mean? Well, what it means directly is he took a card and then he didn't put it back. But what the implication is, I'll say thus: what you draw on the second, or what you draw second, or what he draws second, or whatever, what you draw second depends, to some extent at least, maybe not a lot, but it depends to some extent. I guess I'll put that in there. Whatever extent it is, depends to some extent on what you drew first. There's a dependence going on here. Get it? Hence the name dependent events. So, in other words, you won't, for example, it will be impossible, probability of 0, you won't be able to draw the same card twice. You can't draw ace of hearts and then ace of hearts if you don't put the ace of hearts back. See what I'm saying? So there is a little bit of dependence on what happened second. It depends a little bit on what happened first. You won't be able to draw ace of hearts twice. Okay, so what are we going to do then? Well, first let me show you this new highfalutin formula. This is cool. I like this formula. Goes something like, let's see, let's write it like this. Probability of, I get an ace first, I'll use a new notation, and an ace second, that's what I mean by that, is you take the probability that you got an ace first, right, just like we used to, and then you multiply, just like you used to, but now you have to multiply not just by this, because the probability that you get an ace second has a dependency on whether you got an ace first, and we represent that by doing this. That little slash A1 there. And this is called, this whole thing, is called a conditional probability. It has a condition on it, right? I always have a hard time with this word. It's called a conditional probability because the probability that you draw the ace second, or actually, let's actually say it this way. It's it's the prob of drawing an ace second, given that, that's kind of what this line represents, this horizontal, this pipe they call it, given that you drew an ace first. Okay, so now when you actually go to do this, you're going to say, oh, that wasn't hard. Okay, you ready? Let's do this in a different color just to try to keep our notes a little bit clear here. What is it? It equals, well, let's look at our deck of cards. Right now I have a full deck of cards and mix them up real good. What's the chance I get an ace? Well, there's 4 aces out of 52 cards, so I don't feel like reducing fractions right now. So I'll say 4 out of 52. That's this. And then I'm going to get another ace. Well, remember, I'm not putting the first ace back, which means one of these aces, who knows which, but let's just say that one's missing. If that ace is missing, now what's the chance I get an ace? Well, there's only 3 left. And by the way, the deck is smaller too. So there's 3 left out of 51. Get it? That's the main point. And to enter this on your calculator, you could do it this way. 4 divided by 52 multiplied by 3 divided by 51. Hit your equals button. And you will get 1 in 221. About a 1 in 221. You could turn that into a decimal and a fraction and a percent if you like. 1 in 221. Cool. So just for comparison, maybe I'll put this in like a green. With replacement, if you did put the ace back, then it would be a 4 in 52 of getting an ace, and then you'd have another 4 in 52 of getting an ace. So you'd have 4 in 52 times 4 in 52. And that, I worked out, came out to 1 in 169. So that's easier than a 1 in 221, right? So it's easier to get 2 aces if you put one back in the deck. If you take one out of the deck, oh, now you've got fewer aces, and so it's a little harder to do. You get the 1 out of 221. Okay, cool. And that is the main point for the day. This idea of dependent events. What happens on the second draw depends on what happens on the first. It's harder to get an ace on the second card if you already drew an ace on the first card. See what I mean? So there's a dependence there. The probability depends on what's already happened. Those are called dependent events. This is called a conditional probability. Cool. Let's see. Oh, here's another example. More cards. More cards. Let's do some more cards. Bonnie randomly draws 5 cards without replacement. You might as well say somebody dealt her 5 cards, right? Randomly shuffled and all that, dealt her 5 cards. Find the probability that all are hearts. Now, if we have any poker players in the audience, this would be like saying, what's the probability that she's just dealt a heart flush? Right away, boom, heart flush. Yeah, a happy thing when that happens. Well, what you got to do is, you got to think like this. It's without replacement. So every time you get a heart, it's going to be a little harder to get another heart. So it goes kind of like this. At first, there are 13 cards in any suit, right? I can come back up to the diagram and prove that to you. If you count across, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. Yep, 13 in any suit. Whoa, let's erase some of this mess here. Okay, so there's 13 cards in any suit. So there's 13 hearts out of 52. Now, assuming that she already got a heart, there's only 12 left, and by the way, there's only 51 cards left. And if she got 2 hearts in a row, well, now there's only 11 left, and it's only 50 cards left. Then there's only 10 hearts left out of 49 cards. Then there's only 9 cards left out of 48 cards. You see how this goes, right? So this comes out to a 33 on top and a 66 640 on the bottom. How do I know that? I know that because I'm using a Casio FX 300 ES. Nice calculator. $15 maybe. You might want to get it for this course because it gives you fractions right away. No muss, no fuss. And then you could just hit the SD button to get it, turn that into a decimal. And if you did, you would get, what do we get? Something like 0.0004952 or something like, I'll just round incredibly, 0.05% roughly. Very close to 0.05%. P.S. Sometimes it's nice to express your probabilities this way. So we've got that 33 out of 66,640. That's kind of a hard number to think about, don't you think? I mean, you know it's small, but it's a little hard to get a grip on it. It's kind of hard to get a grip on that. Hey, how big is that? You know, it's small. Okay, well, how big is that? Well, you know, it's small. See what you think of this. I take the fraction form here, and I'm going to kind of reduce it in a way. You know how you can divide the top and bottom by the same thing? Well, I don't care if 33 goes into the top and bottom evenly. I'm going to do it anyway. I'm going to divide top and bottom by 33. What that does is it forces the top to be a 1. Get it? And then the bottom is not going to come out even, but it comes out, if I round to 1 decimal place, it comes out to 2019.4. And so, hey, this is saying roughly 1 in 2,000. You can think of that. 1 in 2,000. I'd have to sit here and get dealt cards 2,000 times, roughly on average, in order to get a flush of hearts. I love that. And by the way, just in case we do have some poker players out here, what would be the probability of getting any flush? Not just hearts, but any flush. Well, there's 4 suits. So it would be 4 times that, which comes out to 1 in 500. So if you sit at the poker table for about 500 games on average, someone's going to deal you a straight flush. Someone's going to deal you a flush right off the bat. Boom, there you go. Notice your chances of getting a flush are even better because usually you get to throw some cards away and all that stuff. But anyway, it's nice to have these numbers in mind. That person over there seems giddy. Gee, I wonder if this is the one time in 500 that they were dealt a flush. Could be if they're that giddy. Whatever. Okay, let's get away from cards for a while. In fact, this is an urn, a good old urn, some kind of a big pot type thing. It's got marbles in it. 4 blue, 4 green, 4 yellow, 4 red. Why don't you try this problem? Bubba draws without replacement and gets 3 yellows. Bubba draws without replacement and gets 3 yellows. Work out those probabilities. Pause the tape, but I'm old. Pause the video. Come on back. Ready for this one? Well, first of all, the probability of just getting a yellow is you would put the number of yellows over the total number, right? This is just going all the way back to lecture, 3 or something? This is how you define a probability. And so when he's just sitting there, he's going to grab one marble at random. Well, there's 4 yellows he might grab, and then there's 4 plus 4 plus 4 plus 4. 4 blue, 4 green, 4 yellow, 4 red. This comes out to a 4 in 16, which reduces to a 1 in 4. So the chance of just grabbing 1 yellow marble is 1 in 4. What about the chance of grabbing all 3? Well, it's with replacement. In fact, let's change the color here. With replacement means puts them back every time, which means it's always a 1 in 4 every single time. So in that case, we would write something like this. The probability of getting yellow, yellow, yellow would be just take the probability of yellow times the probability of yellow again times the probability of yellow again. So that's a 1/4 times a 1/4. I guess I'll write it out. Times a 1/4. You could say 1/4 to the 3rd power, of course, and you get a 1 in 64. Now that's with replacement. That's supposed to be circled, not crossed out. With replacement. 1 in 64. Part B is saying without replacement. So now you have to take into account that it's going to be harder to get another yellow one if you already took 1 yellow out of the pot, the urn, so to speak. So I'm going to write this just to give you some sort of a notation that you might like to use. That the probability... Oh, let me write it this way. Let me use that color again, in other words. So the probability of... Now, I like to put little subscripts here when I'm doing these dependent events. Yellow 1, yellow 2, yellow 3 is going to be, well, first you got to get a yellow on the first try. Then you need to figure out the probability of getting a yellow on the second try, given that you just got a yellow on the first try. And then you'd have to multiply by the probability that you get a yellow on the third try, given that you already got yellows on both the first and the second tries. That's the formula. Now, formulas are not really there for memorizing. They're there to help you kind of understand the flow of what's going on here. Here's what's really happening. The probability of getting a yellow on the first shot, well, it's the same as up here, 4 out of 16. I'm not going to use a reduced fraction here. And the reason I'm not going to use a reduced fraction is because it makes the next thing easier to figure out. There were 4 marbles, but we got 1, so now there's only 3 left. There were 16 total, but we took 1, so now there's only 15 left. See? This would correspond to the probability of getting a yellow second under the condition that you already got a yellow first. Next, we're going to get another yellow. Well, there's only 2 left now, 14 in the urn, right? So if you work this out, this comes out to a 1 in 140, which means if you compare these two numbers, it's a lot harder. It's more than twice as hard to get 3 yellows if you're not putting them back, or I should say maybe it's twice as easy if you do put them back, or however you want to say it. The ratio is not exactly 2 to 1, but roughly. Okay, cool. All right, okay. 2 people are randomly selected from the birthday. Oh, I was supposed to change this example and I didn't. Darn it. Really? Really? I was supposed to change this example. I hope you don't mind if we just change it on the fly here. Let's change it as we fly. I'm going to say, cross this whole thing out. I don't like the birthday. I wanted to talk about the birthday problem because you might remember it from the previous lecture. But actually, to make this discussion a little bit more precise, let's change the example. I'm going to say assume 50% of the general population will vote for Biden, or how should we say that? Is a Biden supporter. I don't know how you want to say it. Is a Biden supporter. They say, oh yeah, vote for him and all that stuff. So if you selected two people at random, so I'll say from the population, what's the probability both are Biden supporters? So this is similar to where we said both are born on June 1st, right? We kind of went like this. We kind of said, well, the probability that, we did it before when it was birthdays. We said, well, there's a 1 in 365 that they're born on June 1st. There's another 1 in 365 that they're born on June 1st. Okay, here we got something different. 50% chance Biden supporter, and then again, 50% chance Biden supporter. If you multiply that out, it's 0.25 or 25%. Okay, now let's bring in a new color because, or in fact, let's bring in a reddish color because, wait, something's wrong here, Batman. Does Robin ever say that? Anyway, something's wrong. And I want you to pause for a minute and try to figure out what's wrong. What could possibly be wrong? Isn't this what we do? We multiply probabilities together? Yeah, that's what we do. We multiply probabilities together. Well, I'll tell you what's wrong. We did a straight, hey, what's the probability of a Biden supporter? Hey, what's the probability of Biden supporter? Right? But this assumes independent events, which itself assumes drawing with replacement, or sampling. Let's put sampling there. Sampling with replacement. That's not really how we do that when we go take a poll. Do we actually, grab somebody at random and then put them back in the population? And then go out again and grab another person? It's not really what we do. What we usually do is we grab a bunch of people, put them in a room or whatever, and then talk to them, right? So it's not what we did. So I'm going to say theoretically, since we draw without replacement, or sample without replacement, we should do something like this. The probability that the first guy is a Biden, or the second's a Biden, is, take the probability of the first one's a Biden, yep, so always start with that, times the probability that the second one's a Biden, given that the first one's a Biden. Now this this is going to be 50%. This, because you didn't put the Biden person back in the population, it used to be exactly 50%. If you took one out, it's got to be a little bit less than 50% now. So it's got to be something like a 49 point, and I'm just going to put a bunch of 9s here. So theoretically, there's a problem here. Let's emphasize that. It's not that there's something really wrong. Theoretically, there's a problem. I hope you see it's not a real problem, because 50% and 49.99999, isn't that basically going to be the same answer? Yeah, it is. No practical effect, I'll put. So we don't worry. We just don't worry. So with polling practices or anytime you're sampling from a large group, we will usually treat things as independent events, even though technically they're not. Because if it's a large population, then this probability only goes down by a tiny little itty bitty squeaky bit. And we don't care. It's not really going to affect our answer. So, it is something you want to be aware of, though. Be aware of this because whenever you're sampling in a smaller group, you're definitely going to say, wait, I can't just do that. I should go back and figure out conditional probabilities, okay? I should go back and figure out this kind of a thing, okay? So just a theoretical point to keep in mind. Okay, I think I have 2 more examples. Yeah, 2 more examples. So changing it up just a little bit. People who major in statistics and stuff, they don't always go around counting, cards and marbles from urns and stuff. They usually have like actuarial tables and other kinds of tables of data that they work with. So here's an example. And this is recent news. So success in college, turns out, it correlates highly with GPA. This is an argument for saying, so why take a placement test? Just use the high school GPA. Okay, this is a very strong political argument made over the past, I don't know how many years. Anyway, it's correlated with high school GPA, and I'm gonna say that this data is correct. It's my approximation, but I approximated it by doing a bunch of Googling. So it can't be that far off. Okay, so let's just assume this table is good. So the question is, if we just go and select a high school graduate at random, just one, what's the probability that this student can graduate within 6 years? I put can in quotes because, of course, it all depends on a million things. So I'd hate to say can't or can or can't. I'd just say will or would or based on averages or whatever, something like that. Anyway, we're going to select one of these students at random, just one. What's the probability that they graduate on time? Okay, well, reading this table, here's high school GPA in 3 ranges. There's 3.75 or higher, there's 1.75 or lower, and there's basically in between. This is the percentage of students graduating high school with that GPA, with that GPA, with that GPA. Okay. Now notice that these numbers here sum to or add to 100%. And why is that? Well, because this exhausts all the possibilities. GPA starts at 0 and ends at 4, and there's no holes here. It's 0 to 1.75, 1.76. That's everybody, right? That's all possible GPAs. And if it's all possible GPAs, then we must have 100% of the students falling into one of these categories, and so that's why it adds up to 100%. Now over here, this is something a little bit different. So what does this say? Percent of college attendees who graduate within 6 years. So it's a 90% chance of graduating within 6 years if you're in this category. You had a high school GPA of 3.75. You're one of these 30%. It's a 62% chance if you're one of these students, GPA in that range, which is 60% of them. And it's a 30% chance graduating in 6 years if the GPA is this, which is this many percentage of the students. Okay, so these numbers over here do not add to 100%. They don't have to. They might by coincidence, but they do not need to sum to 100%. They're unrelated to each other. Unrelated to each other? Yes, they are. Because this is related to this, really, to these people. This number is related to these people. This number is related, the dependency goes this way. It doesn't go the other way. So those don't add to 100%. We don't have to worry about that. But often you do want to keep an eye out. Like sometimes things should add to 100%. And you can just spot check that they do. If these only added to 90%, you'd say, hey, you're missing some data, buddy. I can't use this. There's data missing, buddy. You want to say it just like that. Anyway, where am I on this thing? Here I am. Anyway, you could think of this in terms of a tree method, right? There's a person going to graduate, or no, there's a person in high school right there. So 3 possible paths. They could end with a high GPA. They could end with a medium, I guess, GPA. They could end with a lowish GPA. Now, in one universe, they end with a high GPA and they go on to graduate, or not. Or in the medium universe, they go on to graduate, or not. And in the low GPA universe, they go on to graduate, or not. Now, I'm just talking about the ones that actually go to college, right? Okay, and what we're interested in for this problem is we're going to pick one of these people at random, right? This person's going to be selected at random, and this person will either have a high GPA and graduate, that's one possibility, or this person will have a medium GPA and graduate, that's another possibility, or this person will have a low GPA and graduate, this possibility. So we've got three paths to get to the final result of graduating, that a randomly selected high school student can graduate within 6 years. So to get this probability, you go with the probability of, well, it's right here, 0.3, right? That's the probability of going to the high. The probability of going to medium is 0.6. The probability of this one is 0.1. Now, if you have a high GPA, it's a 0.9 that you graduate from here. If you have a medium, it's a 0.62 grabbing it from here. And if you're a 0.1, it's a 0.3 that you graduate grabbing it from here. So remember the multiplication rule yet again. So this is a 0.3 times a 0.9. This is a 0.6 times a 0.62. This is a 0.1 times a 0.3. And you add these up and you end up with, what I get? 0.672. That would be your answer. 67.2%. Something like that. Now keep a critical attitude in a statistics class or in any situation in life. Keep, what's the word? I don't want to say cynical. What's the word I want to use? Keep a critical? Keep your critical thinking cap on. Keep a critical thinking cap. How's that sound? Turns out there's lots of like standard ways to criticize data or standard ways to question and say, I wonder if this is an issue. I wonder if that'd be a better way to say it. There's like a typical set of issues that could come up in any data set. That was the way to say it. One issue that comes up a lot is a time factor. Time factor. In any table of data like this, where's time? There's no time, right? What do I mean by a time factor? Well, in 1990, the average GPA of all high school students was 2.6. In the year 2000, the average GPA of all high school students was 2.9. Can you say grade inflation? In the year 2020, the average GPA of all high school students was something greater than 3.0. That's a greater than sign. Greater than 3.0. So GPAs are going up over time. And so that would suggest that you got to keep in mind this data is going to change. GPAs are going to be shifting this way over time. And as they shift this way, how are these numbers going to change? Are they going to shift in the same way? Are they going to remain constant? Are they actually going to shift the other way? You know, you have to keep in mind that this is not static situation. This is just a right now, and it might only be good for like a couple, 3 years or so, right? So anyway, when you're making policy decisions, you want to ask these kinds of questions. Okay, so one more. There you go. Why don't you try this one? Read this out, try to figure out what's going on, and then try to answer it. Ready to go here? According to the table below, what's the probability that a random selected commuter arriving before 9, because they're all arriving before 9 here, arriving before 9, finds a good parking spot? Okay, so 20% of the commuters are arriving before 6:30, and they all have a 98% chance of finding a good parking spot. So if you happen to choose one of those 20% arriving before 6:30, they will have a 98% chance of finding a good parking spot, right? So the probability of getting from here to here is 0.2 times 0.98. And then another 20% are arriving at, well, between 6:30 and 7. And so to get to there, 0.20 times, boy, that's nasty looking. 0.20 times 0.94, it looks like. That's a 9. And then here's another independent path that you could take. So it's 40% of them have an 80% chance. And then this last 20% of them have a 5% chance. You just multiply that all out, you get a 0.714, or about a 71.4%. Hope you enjoyed it. Okay, let's see how long did I take this time? 35 minutes. Okay, still not too bad.